Hi class, this is an example problem for unit 4.1 in which we learn about moments of the force in two dimensions. So I took a problem from the book, edition 13, it's problem 4.7. And in the book, the diagram looks like this. Basically, we have an L-shaped bar and there's three different forces acting on it. So up here, I've redrawn that as best I can. We have these three forces. Force one, that's acting at 30 degrees from vertical, 250 newtons. Force two, 300 newtons, it's 60 degrees from horizontal. And then we have force three, it's 500 newtons, and we're given this 3, 4, 5 triangle. Point A is over here, there's point B over here, and we're given all the dimensions. And what we're asked to find is the moment about point A. So in two dimensions, typically we can just solve for the moment by looking at the force that's acting and the distance that it's from the axis that it's acting at. So force times distance. And you can only multiply forces and distances that are perpendicular to each other. And then when it comes to moments, we define a twist that's in the counterclockwise direction as being positive, and twist that's in the clockwise direction as being negative. So you may recall hearing a little bit about the right-hand rule. And so the way I like to think about it is when I think about right-hand rule, I'm pinning my wrist on the point that I'm rotating about, and then I point my fingers towards the force that's going to cause the twist, and then I bend my fingers to point towards the force, the direction that the force is acting. And then the way that my thumb is sticking, if it's sticking out of the board, that's positive. If it's sticking into the board, that's negative. So I'll demonstrate that as we go through this problem. So in this case, we have, force A, and we're trying to find the moment about point A caused by all of these forces. So the way I'm going to do is I'm going to look at the moment caused by each force one at a time, and then we can add them all up at the end. Moments are just like forces, you can add them when they're in the same direction. So first off, I'm going to say the moment about point A caused by force one. That's going to equal, so let's think about that. So it's going to be the force one is acting downwards. So if I were to do my right-hand rule, I pin my wrist at point A, and if I go the horizontal travel distance, and then I'm going to curl my fingers, point my fingers towards the direction that force one is acting, it's going to be down. And so that's going to cause, you can kind of just tell, right, a clockwise twist, and that'll be a negative. So we're going to have negative F1y times the horizontal travel distance, dx. And in this case, even though F1 has an x component, that x component lines up with point A. And so even though there's an x component there, the travel distance is 0. So its contribution to the moment is 0. So I can rewrite this as negative F1 cosine, which I guess I know what F1 is, it's 250. So negative 250 cosine 30 times 2. And when I plug that in, I get that in. The moment about A caused by force 1 is going to equal to negative 433 Newton meters. And the negative tells me that it is in the clockwise direction. Only one has 1 because I'm going to come back to it. Now, MA2, the moment about point A caused by force 2. Similarly, we're going to look at this, and so we pin our wrist to point A, you point it towards from from point A to where that force acts. And since we're looking at the horizontal distance, we're looking at the y component of the force, and that is going downwards. So our twist is going to be clockwise. My thumb's pointing to the board, and that is a negative moment. So we get negative F2y times the horizontal travel distance. And that's going to be minus 300 times sine 60. And the distance is 5. And that ends up getting me negative 1,299 Newton meters. So again, that's clockwise. We'll label that as round 2. I'll come back to that. Now, the moment caused by F3 is a little bit different because it doesn't act right along this line where A is. It's over here. The X and the Y components of that force are going to cause a moment. So MA3. So let's start like we had before. Let's look at the horizontal travel and the vertical force. So pin my wrist at point A, my fingers travel along the horizontal travel, and the Y component of F3 acts along here, right, at point B, so this line of action. And it's going down. So once again, it's going to cause a negative moment. So we get negative F3y times that horizontal travel distance. But here, there's also an X component of the force, and that X component of the force doesn't line up with the point. So now, when I pin my wrist at point A, oh, this is hard. My wrist doesn't bend that way. And then I'm going to my fingers are going to go downwards along the vertical travel. And then the X component of this force acts along this line, going through point B. And it's going to the right. So my fingers end up curling to the right, and that's going to be a positive moment, right? You kind of thought that would cause a positive twisting. So I get plus F3x times that horizontal travel distance. So that would be negative 500. And so this is the y, so it's 4/5. And then the horizontal distance we went was 5. Then positive 500 times 3/5. And that vertical distance we went was 4. And when I do all the math, I get that force 3's contribution is negative 800 Newton meters. And so I know that my total moment about A is just going to be MA1 plus MA2 plus MA3. That's equation 4. So I'm just going to plug sub 1, 2, and 3 into 4. And I end up getting that MA equal to minus 2,532 Newton meters. So once again, in 2D problems dealing with moments, you can just use this force times distance equation. And where if the force, if you're looking at the X component of the force, you have to multiply it by the X distance from the point that you're rotating about. And if you're taking the X component of the force, you multiply it by the Y distance from the point you're traveling about. And that distance always goes, right, you're always looking at the distance from the point you're rotating about to where that force acts, to where the force is, the line where the force is acting along. And then you use the right-hand rule to determine if the force is positive, or if the moment is positive, or going in a counterclockwise direction, or if it's negative and going in a clockwise direction. So hopefully that's helpful and makes some sense, clears up a few things about how to find moments in 2 dimensions.